If you work in IT or you're trying to get into IT, there's a very real risk in 2026, and that is spending time learning technologies that are slowly becoming less relevant. Traditional firewalls, VPNs, passwords, and networks are not disappearing, but how we design and secure them is changing rapidly. In this video, I'm going to walk you through the networking and cybersecurity technologies that will actually matter in 2026 and beyond. Let's get started. For a long time, security was built on a very simple assumption. If you're inside the network, you're trusted. And if you're outside the network, you're not. This made sense when users worked from offices, devices were company-owned, and applications lived in corporate data centers. Zero Trust completely changes this assumption. In a zero trust model, nothing is trusted by default. Not users, not devices, not locations, and not even traffic coming from inside the network. ZTNA model, or Zero Trust Networking, assumes breach by default. Every access request is continuously verified based on identity, device posture, and context. This means that even if an attacker gets inside the network, they still can't freely move around. In practical terms, Zero Trust often replaces traditional VPN with identity-based access to specific applications rather than the entire networks. This shift reduces the attack surface and aligns security with the way modern cloud and remote work environments work. As organizations moved their applications to the cloud and users started working from anywhere, a big problem surfaced. Forcing all traffic through a central office network created performance issues, added complexity, and left security gaps. That's where SASE, or Secure Access Service Edge, comes in. SASE combines networking and security services, all delivered from cloud. Instead of users connecting to a VPN and routing traffic through a central office, they connect to a nearby cloud security edge device. This edge device checks security policies before granting access to applications, boosting performance, cutting down on latency, and simplifying the overall system. But SASE doesn't just secure cloud applications. It also ensures safe access to on-premise custom applications. Whether it's cloud or on-prem, SASE provides consistent, streamlined security. The security part of SASE is handled by something called SSE, or Security Service Edge. This focuses on things like secure web gateways, cloud access security brokers, and zero trust access. Together, SASE and SSE represent a major shift from traditional hardware-based security to cloud-native security, designed for how we work today. One of the biggest challenges in modern IT environments is scale. Networks, cloud platforms, and security systems generate massive amounts of telemetry data every second. Logs, alerts, metrics, and events can quickly reach volumes that humans simply cannot process effectively. AI-driven network and security operations use machine learning models to identify patterns, detect anomalies, and reduce noise. Instead of overwhelming engineers with thousands of alerts, AI systems surface the small number of issues that actually require human attention. This does not mean engineers are replaced. It means they can focus on decision-making instead of manual analysis. By 2026, AI-assisted operations will be essential not because they are trendy, but because modern environments are too complex to manage manually at scale. Encryption is the foundation of modern security, protecting everything from web traffic to cloud storage and identity systems. However, the rise of quantum computing introduces a long-term threat to many of the cryptographic algorithms we rely on today. A sufficiently powerful quantum computer could break commonly used encryption methods that are currently considered secure. Even though large-scale quantum computers are still developing, the risk already exists because encrypted data captured today could be decrypted years later. Post-quantum cryptography focuses on designing algorithms that remain secure even against quantum attacks. Governments, financial organizations, and cloud providers are already planning migrations to post-quantum algorithms because cryptographic transitions take years. This is a forward-looking area of security that highlights how proactive planning is becoming essential. Passwords have consistently proven to be one of the weakest elements of cybersecurity. They are reused, phished, guessed, and stolen at massive scale. As a result, the industry is moving towards passwordless authentication using passkeys, biometrics, hardware-backed credentials, and strong multi-factor authentication. In modern architectures, identity becomes the primary control plane for security decisions. Instead of trusting a network location, systems evaluate who the user is, what device they are using, and the risk associated with the login attempt. This approach aligns well with zero trust principles and cloud-native environments. In 2026, understanding identity systems will be just as important as understanding networking fundamentals. Networking is following the same transformation that servers and storage went through over the past decade. Instead of relying heavily on physical hardware configurations, networks are increasingly defined and managed through software. Software-defined networking allows administrators to control traffic flows, segmentation, and policies programmatically using APIs and automation. Network as a service extends this concept by delivering networking capabilities on demand through cloud platforms. This enables faster deployment, easier scaling, and tighter integration with DevOps workflows. For engineers, this means networking skills are increasingly blending with software, automation, and infrastructure as code. Traditionally, data protection focused on encryption at rest and encryption in transit. However, data was typically decrypted while being processed in memory, creating potential exposure. Confidential computing addresses this gap by protecting data even while it is in use. This is achieved through hardware-based trusted execution environments that isolate sensitive workloads. Confidential computing is particularly important for cloud environments where customers want strong assurances that their data cannot be accessed by unauthorized parties. As cloud adoption continues to grow in regulated industries like healthcare and finance, confidential computing will play a key role in building trust and enabling sensitive workloads to move to the cloud. Security tools have historically been deployed in silos, with separate solutions for endpoints, networks, email, cloud workloads, and identity. This fragmentation makes it difficult to see the full picture during an attack. Extended Detection and Response, or XDR, aims to unify security telemetry across multiple domains into a single platform. By correlating signals from endpoints, networks, cloud environments, and identity systems, XDR provides better visibility and faster response. Attacks today are often multi-stage and span multiple systems, so this unified approach is increasingly important. XDR represents a shift towards holistic security rather than isolated solutions. The most important takeaway from all this is that networking and cybersecurity are no longer about defending a fixed perimeter with static rules. The future is identity-driven, cloud-native, software-defined, and increasingly assisted by artificial intelligence. This does not mean foundational knowledge is no longer important. It means fundamentals are being applied in new ways. Engineers who understand these emerging concepts will be better positioned to adapt, learn new tools, and remain relevant as the industry evolves. Instead of chasing individual products, focusing on these architectural trends will provide you a long-term career value. That is it for this tutorial. We hope you learned something new. If you did, please consider liking this video and subscribing to our channel. We will catch you guys in the next one. Until then, take care and have a good day.